Download this code from codegive.com, link in the description below. OK, let's dive into semantic analysis in compilers, covering its purpose, steps, and providing code examples to illustrate the concepts. What is semantic analysis? Semantic analysis is a crucial phase in the compilation process that follows lexical analysis and parsing. While lexical analysis tokenizes the source code and parsing creates a syntax tree, usually an abstract syntax tree or AST, semantic analysis goes deeper to ensure that the code actually means something valid and meaningful according to the programming language's rules. It checks for errors that are not caught by the earlier phases, focusing on the meaning and consistency of the program. Key goals of semantic analysis *. 1. Type checking * verifies that operators and functions are used with operands of compatible types. For example, it prevents you from adding a string to an integer, unless the language explicitly allows for such implicit conversions. 2. Scope resolution * determines the declaration that corresponds to each use of a variable, function, or other identifier. This is often done by building a symbol table. 3. Name resolution – identifier binding resolves identifiers to their declarations. Similar to scope resolution, but focuses on associating each usage of a name with the correct entity. 4. Flow of control checks * ensures that control structures, loops, if-else statements, are used correctly. Examples include * checking that break statements are only used within loops or switch statements. * verifying that all functions with a non-void return type have a return statement on every possible execution path. 5. Uniqueness checks * ensures that identifiers, example variable names, function names, are declared uniquely within their scope, preventing naming conflicts. 6. Initialization checks * verifies that variables are initialized before being used. Some languages enforce this strictly. 7. Constant folding * evaluates constant expressions at compile time to improve runtime performance. For example, replaces x equals 2 plus 3, with x equals 5. 8. Liveness analysis * a more advanced technique used in optimization to determine which variables are live, i.e., their values might be used later, at any given point in the program. Steps in semantic analysis *. Here's a typical sequence of steps involved in semantic analysis. 1. Build symbol table *. The symbol table is a data structure, usually a hash table, that stores information about all identifiers, variables, functions, types, etc., used in the program. Each entry in the symbol table typically includes * identifier name, * data type, * scope, * location in memory, for variables, * number and types of parameters, for functions. 2. Type checking * traverse the AST and perform type checking on each node. This involves * determining the type of each expression, * ensuring that operators are applied to operands of compatible types, * checking the types of function arguments against the function's parameter types, * performing implicit type conversions if allowed by the language, * reporting type errors if type mismatches are detected. 3. Scope resolution * traverse the AST and resolve the scope of each identifier. This involves * searching the symbol table for the declaration of the identifier in the current scope. * if the identifier is not found in the current scope, search the parent scopes until the declaration is found or the top-level scope is reached. * reporting an error if the identifier is not declared. 4. Other checks * perform other semantic checks, such as flow of control checks, uniqueness checks, and initialization checks. Code example: Python A simplified semantic analyzer. Let's create a simplified semantic analyzer for a very small language that supports variable declarations, assignments, and basic arithmetic expressions with integers and booleans. This example will illustrate symbol table construction and type checking. Explanation asterisk. 1 Symbol table class asterisk. Asterisk implements a symbol table using a dictionary, self.table. Asterisk insert, name, type, adds a new entry to the symbol table. Asterisk lookup, name, searches for an identifier in the current scope and, if not found, recursively searches parent scopes. Asterisk create _ child _ scope, creates a new symbol table that is a child of the current table, allowing for nested scopes. 2 AST node classes asterisk. Asterisk represent different types of nodes in the abstract syntax tree, AST. Asterisk each node stores information relevant to its type, example variable name, operator, value. Asterisk type, a field to store the type of the expression /node, determined during semantic analysis. 3 Semantic analyzer class asterisk. Asterisk symbol _ table, an instance of the symbol table class. Asterisk analyze, AST _ root, starts the semantic analysis process by calling visit on the root node of the AST. Asterisk visit, node, a recursive function that traverses the AST and performs semantic checks based on the node type. It dispatches to more specific visit _ methods. Asterisk visit _ declaration, node, checks if the variable is already declared in the current scope. If not, it inserts the variable into the symbol table. Asterisk visit _ assignment, node, checks if the variable has been declared. Then visits the expression on the right-hand side of the assignment to determine its type. Finally, it checks if the type of the expression matches the declared type of the variable. Asterisk visit _ binary _ op, node, visits the left and right operands of the binary operation. Checks if the types of the operands are compatible. Determines the type of the result of the binary operation. Asterisk visit _ variable, node, checks if the variable has been declared. If so, it retrieves the type of the variable from the symbol table. For example usage asterisk. Asterisk creates an AST for a simple program. Asterisk creates a semantic analyzer instance. Asterisk calls analyze to perform semantic analysis on the AST. Asterisk includes a try, except block to catch and report semantic errors. Key improvements and extensions asterisk. Asterisk error reporting asterisk improve error messages to provide more context, example line number, column number, and make it easier to understand the error. Asterisk more data types asterisk add support for other data types, example floats, strings, arrays, user-defined types. Asterisk functions asterisk add support for function declarations and calls. This will require asterisk storing function signatures, parameter types and return type, in the symbol table. Asterisk checking that the number and types of arguments in function calls match the function's signature. Asterisk handling return statements. Asterisk control flow analysis asterisk implement checks to ensure that break statements are only used within loops or switch statements and that functions with non-void return types have a return statement on every possible execution path. Asterisk type inference asterisk implement type inference, where the compiler can automatically deduce the type of a variable based on its usage. This is common in languages like Python and JavaScript. Asterisk object-oriented features asterisk add support for classes, objects, inheritance, and polymorphism. This will require more sophisticated symbol table management and type checking. Asterisk intermediate representation, After semantic analysis, you can generate an intermediate representation, IR, of the code. The IR is a platform-independent representation of the code that is easier to optimize and translate to machine code. Examples of IRs include 3-address code and LLVM-IR. Beyond the basics. Attribute grammars. A formal way to specify semantic analysis rules. They are often used to automatically generate semantic analyzers. Static single assignment, SSA, a form of intermediate representation that simplifies many optimization algorithms. Data flow analysis. A collection of techniques for analyzing the flow of data through a program. Used for optimization, verification, and security analysis. Abstract interpretation. A more advanced technique for static analysis that can be used to prove the absence of certain types of errors. In summary, semantic analysis is the phase of compilation that bridges the gap between syntax and meaning. It plays a crucial role in ensuring the correctness and reliability of software. The example above is a starting point. Building a full-fledged semantic analyzer is a complex task, but understanding the underlying principles will give you a solid foundation.